as soon as it starts recording something. Okay. This results tab is also where you would analyze your data. So if you were to have a copy of this on your laptop, for example, you will not have the experiments tab. I don't think you'll have the history tab either. You'll just have the results, basically, so that you can open up your file and analyze your data. Okay. So just as an example, I have some example files down here. So this is just an example of some data. This is a PET, polyethylene terephthalate. This is basically what your water bottles are made out of. It's a pretty nice polymer to work with in that it's pretty stable, and you can sort of control its crystallinity. It is a semi-crystalline polymer. It's pretty easy to control its crystallinity using the DSC. So it becomes a very nice example to show. As you can see here, they did use a heat-cool-heat function. So you can see that there's 3 sort of mini files right in there. Okay. So what I can do, as opposed to looking at all 3 of them in here, I can pull each one out individually. So to do that, I can right-click and say Send to New Graph. And this will just be the first heating scan of that material. Okay. And you can see that's much easier than looking at all of this and trying to figure out which part am I on. I mean, the program also, does color coding and things like that, but you still don't want to sort of have all of this, looking at all of this at the same time. This is a lot easier to look at, right? So going from low temperature to high temperature, of course, we have the glass transition, which basically looks like a step. Doesn't always look like a step, but it should look like a step. And then we have the crystallization function. In this bottom left corner, you would see it says exo up. That means exothermic reaction should point upwards, endothermic reaction should point downwards. So anything that releases heat should point upwards. Anything that absorbs heat should point downwards. I can flip this if I want to. You would see people, instead of showing your heat flow, they would show heat capacity. We can change our y-axis by simply right-clicking and going to select variables. And you have up to 4 y-axes that you can show at the same time, but you only have 1 x-axis. So typically I leave the x-axis in temperature. So y1 right now, it's my normalized heat flow. I can switch that to normalized heat capacity by simply checking and unchecking the boxes right in here. And I can hit OK. And now you would see that things are flipped, right? It's flipped because heat capacity can never be negative. So everything should be in the positive regime. And when you're doing crystallization, it will look basically upside down to where it should look. And so basically you would see some literature post everything in terms of heat capacity. I kind of like heat flow for a sort of more standard analyses, simply because the units would make sense to more people. So if I go to analyze any one of these transitions, I have an entire analysis tab up here. And I click on that. And on this drop-down box right here, I have an entire list of functions that I can use to analyze my data. Not all of them necessarily apply to this data set, but again, I have the ability to do all of these things essentially in this software. I can fit things to straight lines or polynomials, exponentials. I can look at signal changes, onset points, peak heights. The first 2 are probably the most important, looking at glass transition temperatures and enthalpic transitions. So the first one is, of course, looking at your TG. The second one is looking at crystallization and melting functions. So in terms of DSC, those are probably the 2 most important ones. The the size for this drop-down box, let's say I just want to analyze my glass transition temperature. What I can do is I can basically click and drag across the temperature region, okay? And then I right-click. And once I right-click, I can say Analyze. And in this Analyze tab is the same list that was up in that top left-hand corner. So I don't have to necessarily go up to that corner. I can simply do a right-click and have the same processes available to me. This is a glass transition, so I'm going to click the glass transition function. And you would see that it made a few things happen here. So first of all, it grayed out everything else except for where my cursors were, which kind of helps you zoom in on what you're actually trying to analyze. In terms of where I place the cursors, you want to make sure that the cursors are not all the way up in here, all the way against the actual transition. You want to step it back onto a nice plateau region if there is one. Sometimes these can be butted up against other transitions, so it may be a little difficult. But if you do have the space, step it back. This helps you get much more accuracy and consistency in the actual measurement. And that occurs for both sides. So what's actually happening here is that it's creating a tangent from this point all the way across, a tangent from this point all the way across, and a tangent from the inflection point of this step, and it's going to sort of cut both of the other tangents. So where this tangent meets this one, that's defined as your onset point. Where this tangent meets this one, down here, that's defined as your end point or your inset. And so you want it to look, optimally it should look like this, where your tangents lay very nicely on that baseline, on their individual baselines. If you go into this mini menu here and say show parameters, you will see that you have a lot of things to play with. I won't go into all of the things that you can play with, but there are a lot. If you would like to, if you're going to download this onto your computers, I suggest definitely going in here and playing and seeing what all these things actually do and how they change the analysis. But what you can do is you could go into the Labels tab and add any information that you essentially want. So right now I have the midpoint type, so how it actually measured the midpoint, the value of that measurement. I can put in now my delta CP, which is sort of the vertical distance between my onset and endset. This is actually in the units of heat capacity as well. I can put in my my onset temperature. I can put in my end temperature, and etc., etc. I go all the way down the list. Okay, and you can see as I check each one of them, they automatically pop up on the graph. And when I have what I like, I hit accept. So you can see now I have all this information on this one transition. Okay, I just defined what the onset and end temperatures were. The midpoint type is basically how it's measuring the glass transition. There are a few ways to do that. I would argue it's much better to be consistent in how you're measuring them, because that way you can compare each measurement to another one. If you change how you measure this, for example, if I do it in the same experiment or on the same sample, you will see that this number itself will actually change, because it's selecting different points based on how you're measuring the glass transition temperature. So the physical number is going to be slightly different. I would not try to argue which one is more accurate, because that can be a very long argument with no real solution, to be honest. So it's much better to just simply be consistent. I personally like the half height method, which is basically half the vertical distance, right? And it basically just cuts it in half, and whatever point cuts across your data, that's your midpoint. That's your glass transition temperature. There's also the inflection point method. There's also the half width method. There's a lot of other methods that can be used. But whichever one you choose, make sure that you are using that for every subsequent experiment, because that could definitely influence what you're doing. Okay. So what we can do now is sort of go on through to the other transitions that we see here. The first one is a crystallization. And again, we can go through the same process. We just simply highlight across that region, right click, and we can go to analyze. And we'll go to the second one, the enthalpy, because now we want to measure sort of the value of the energy of that peak. Okay? So if you click on that, this one is a slightly different function. So what it does here is that it's actually going to create a baseline or draw a straight line between the two cursor points. And again, I can go to show parameters, and you can see that you can do a lot of changes in here. You can split this peak up into pieces and do all sorts of other things. You can add a ton of different labels. All of these functions are there for you to play with on your own time. But essentially, let's just hit accept. What we're seeing here is what it physically did is that once it created this baseline, it's actually measuring the area between your real data and that baseline. So this area in here is represented by this value here. It's called your enthalpy. This value will come in to be very handy once I measure the melting point, and you'll see why in a second. The other thing that it does is that it looks for the peak temperature, so basically that the highest point on that curve and what temperature that is. Typically that's defined as your crystallization temperature. Some people prefer to use the onset, which is here. Again, matter of preference, also matter of application. It depends on what you're going to do with that number afterwards. But you know, all of these are have varying importance depending on the study that you're conducting. So the final transition over here, we're just going to, again, repeat what we were doing. Go to Analyze, Peak Integration. And we're going to go to Accept. Okay, so now it did the same thing. Measured the area in here between the baseline and your real data. Gave you this number. Gave you also a peak temperature down here. Okay? Now, if I were to ask the question of what's the crystallinity of this material before I put it into the DSC, right? Which is a question that it's asked a lot. So the first thing you have to consider is that while I was testing the material, it crystallized. Okay? So now I have more crystals there than I had when I started. Right? Right? So because this entire peak represents crystals that were formed during the experiment. I was asking what crystallinity did I have before the experiment, right? So I have, let's say I had crystals before the experiment, now I've added more, right? And then all of those crystals now are going to melt, assuming that they're all of the same type, they're all going to melt here, okay? So how do I figure out how many crystals I started with? I have to subtract this number from this number. And that's why you would see here it says normalized and signed. Normalized just means it's divided by the mass of the material, so it becomes an intrinsic property. And signed means positive or negative, like these are. Okay? So anything that's above the baseline is positive, anything below the baseline is negative. Okay? And because we have this convention here of the exothermic up, anything that's negative is corresponding to melting. Anything that's positive is corresponding to crystallization. So if I subtract these numbers, or add them in this case, you would see I only am left with about 1 joule per gram, right? And that would be negative 1 joule per gram. So I literally have very little crystals in the beginning, if any at all. 1 joule per gram, especially in this case, of this material is a very, very small, if not negligible number. I generally allow for about 1 joule per gram difference in terms of variation. So something that ends up being 1 joule per gram for most things, especially for things that have very large melting energies, it's not very significant. So if I would say, so if I ask the question of what was the crystallinity before I started this experiment, then my answer would be it was not crystalline. It was a completely amorphous material. Because all of the crystals that were formed here represents all of the crystals that melted here. So in the beginning, there were no crystals. Okay? So that's one of the analyses that you can do. This is a very common analysis. This is anything that's semi-crystalline, you always want to ask how crystalline is it. So this is a very common analysis that you would be doing if you're running something that's a semi-crystalline material.
So if I want to know the crystallinity percentage, that will be the
right.
divided by.
Right. So if you wanted the percentage of crystallinity, so this would give you a value for sort of the amount of crystals that were there in the beginning in terms of energy. If you're looking at percentage or fractions of the whole, you would have to divide that number by what's called the enthalpy of fusion of this material. That's basically the energy, so this value here, that's required to melt a full 100% crystalline sample of the same material. Okay? Now, from a physical perspective, that's actually impossible, right? But there are calculations and experiments that have been done to evaluate what that number actually is. And for many, especially for more common polymers, you can basically look them up. There are polymer handbooks and other guides that you can, or just simply Google them, and you will find these numbers. In case of PET, that number is around 125 joules per gram. So 1 divided by 125 is nothing. So, it's 0.01% crystalline, which is really not crystalline. Okay? So that's why I said that 1 joule per gram doesn't really end up meaning a lot, especially for a polymer like this. Now, if your polymer's enthalpy is extremely small, maybe 50 or something like that, now 1 joule per gram means a lot more, right? So you have to be mindful of sort of where you are with respect to the enthalpy of fusion of the material that you're testing, okay? But that is how you would calculate the actual crystallinity, is that you divide the sum of these numbers by the enthalpy of fusion and times 100, and that would give you your percentage crystallinity, okay? So in this case, like I said, it's basically not crystalline at the beginning, okay? Now this is just the first heating scan. This was just the first step of a 3-step program, and yet I can get all of this information. So you can basically repeat this for the other 2 steps if you want to. If you only cared about your first heat, then this is it. But what I would show is, let's just take a quick look at the cooling step. Now you're actually going in this direction. So you're going from 300 and you're going down, and you can see that it started crystallizing. Okay, so I was cooling at 10 degrees per minute. So at 10 degrees per minute, this material can crystallize. Okay, and then of course we have our glass transition stepping off right there, and then nothing. Okay. Now, how does this change my second heating? If I look at my second heating, now it looks different. Okay, so now I can still see a glass transition, but it's very, very different to what I was seeing before. And I no longer have the peak in the middle here, okay, but I do still have my melting. Okay, so what happened? Well, first of all, it crystallized while it was cooling. Okay, so if it crystallized while it was cooling, then there is no need for it to crystallize again, at least in this case, right? So that's why this peak is now gone, because the material is already crystalline when I started heating it up, which would be different to the first one, where when I started heating it up, it wasn't crystalline at all, so it had to crystallize a bit later, okay? So that's the first thing. And of course, because it has crystals in it, those crystals are going to melt, so you see your melting peak. Now, what's also different is that the glass transition is a lot smaller or harder to make out than this one is. That's because the glass transition is describing sort of how disordered your material is, right? Whereas your melting is describing how ordered your material is. So they're opposites of each other, okay? So if I have a more crystalline material, then I have a smaller glass transition temperature, or a smaller glass transition signal, because less of my material is going to go through that process, okay? Now, if I have no crystals at all, then my entire material is going to go through this glass transition temperature, and I'm going to have a big signal. So that's basically what's happening here, because when we did this calculation, we knew that it wasn't crystalline at all. So this glass transition is nice and big and easy to see, whereas this glass transition is not so big, because it has crystals in it already, so that cut down the total amount of material that can go through the glass transition at the other end. Okay? But again, we can do the same analyses, highlight our transitions, go to glass transition. I'm going to add the same sets of labels that I had on the first one, and we can sort of do a quick comparison. Okay, so before I had my midpoint was 76.7. Now I have 79.4. So it's increased a little bit. Okay. Also, my onset and end have changed as well. Right. So you can see that a lot of things have changed by just looking at the glass transition temperature. Right. The delta CP, so that's sort of how big this step is. You can see it turned from basically 0.38 to 0.17. So just about half, if not a bit more, right? So it's definitely completely sort of converted how this glass transition looked by the fact that it crystallized during the cooling step, right? The one part I would mention here for your melting is that if I were to just give this a